So what's the importance of learning circular motion? See, the thing is, with the concepts of the circular motion, you'll be able to actually understand the amusement parks. The very first thing that you will be able to understand. Hello, Ryan. Can you hear me?
Yeah.
Yeah.
Yeah. I can
You'll be
hear you.
able to understand the mechanism of the roller coaster rise, Ferris wheel, then merry-go-round. Okay, like all these kind of curves. Besides that, like you'll be able to understand the mechanism and the importance and like the engineering behind the speed breakers, like the Formula One bikes, like why the elevation is important on the edge of the road. Okay, like the like a lot of things in the civil engineering. Okay, you'll be able to understand the universe, the gravity with the ideas of the gravitation. You'll be able to understand the launching of the satellite. You'll be able to understand uh, the different Kepler's laws, right? So all that stuff we will be able to understand with the concepts of the circular motion. Okay,
Yeah.
let me tell you one thing. With the circular motion, we will be learning something about the Newton's law of gravitation also in this particular topic itself. Okay,
Yeah.
which can help you in understanding the Einstein's field equation also, to understand the universe, to understand the black hole, to understand
You
the
mean
naked singularity, all that stuff.
You mean the relativistic model of gravity?
Absolutely.
Okay.
Okay, so so all these things can be actually easily understood, right, with the circular motion. So it is that kind of important topic. Okay, so let's talk about first of all the circular motion. What is the circular motion? So very simple. It is actually the motion of an object along the circumference of a circle. As simple as that. Yeah. But circular motion we'll be learning in two parts. One, UCM, that is uniform circular motion. Another one is non-UCM, that is non-uniform circular motion. Obviously, this is basically the vertical circle. Okay, this is the vertical circular motion.
In this case, yeah.
So we have this vertical circular motion in our syllabus, and this UCM is like simple uniform circular motion, where we say that the speed is constant. Okay, speed is constant. Okay, now even if it is circular motion, even if it is uniform circular motion, we are saying the speed is constant. But is it a uniform motion?
Yeah, the velocity stays uniform, the direction changes and is always perpendicular to the center of the centripetal force.
See, the thing is, the velocity keeps changing. It is basically the tangential velocity. Okay, so basically the magnitude is same, but the direction is different. Okay, and then we can definitely say that it is an accelerated motion because it is changing the velocity. Okay, since it is changing the velocity, changing velocities, right? So even if it is having the same magnitude over here, magnitude over here, all same, equals to v, equals to v, equals to v. Here also the magnitude is equals to v. So changing velocity because of changing directions. Now, if it is changing velocity, that means it is an accelerated motion, right? It is an accelerated motion. It is an accelerated motion. So if it is an accelerated motion, that means acceleration is not zero over here. Correct? Acceleration is non-zero. You agree?
Yeah.
If acceleration is there is one more thing. What's that?
Force.
Absolutely. So force is also there. So there is a specific kind of force which basically keeps the object moving in the circular path. Okay. And that force, yes, absolutely. The force which keeps the object moving the circular path is known as the centripetal force, right? Yeah. So we'll be learning, like, in fact, like we have to learn all the details about like about the centripetal acceleration, centripetal forces. Okay, and then we'll be doing some kind of questions also. Okay, so let's do all of them. Let's further describe the uniform circular motion. Uniform circular motion, yes, it is having the constant speed. Okay, it is having the constant speed. Speed is the magnitude of the velocity. Okay, so there is another term over here, and that is the angular displacement. Okay, so there is something called linear displacement that is denoted
And
by
angular.
letter S, is the R. Yeah. So S is basically the linear distance, I would say, is the linear distance. Yeah. And this theta is the angular displacement. Okay. Is the angular displacement. Okay. You already know that S is equals to R theta, right? Yeah.
Yep.
Okay, so S is equals to R theta. So, so if I write derivative of S with respect to time, so I'll write R is a constant, d theta over dt. Now, how do we define this ds by dt as v? Have you done derivatives?
Yep. Yeah.
Yeah. So v is equals to R d theta over dt. So what is this d theta over dt? Is the rate of change in the angular displacement.
So
right?
angular velocity.
And that's known as the angular velocity. This is
I think I think I did some of this stuff with Fahid, sir.
All right. Okay, that's great. So this is v is equals to r omega. Okay, so we have this stuff. So should I focus on the questions then?
Yeah, maybe, or maybe we could look at more interesting or complicated parts. I was actually probably more interested in rotational mechanics, since that seems a little bit more
in depth. The rotational mechanics. Unfortunately, we don't have it in our syllabus, though it is there in the options.
Yeah, but it's option. Yeah, exactly. So if we could go over that, that'd be cool.
Okay, yeah, sure. So the thing is, okay, let me bring in a little bit of the rotational dynamics over here. Okay, so here when you are considering the linear motion, okay, we call it translational motion basically. Okay, so this is the translational motion, and then we are having the rotational motion. Okay, rotational motion. All right. Now let me tell you one thing. Here I'll be talking about an acceleration in the rotational motion, but it's not same as the centripetal acceleration. Okay, I'll tell you the difference between both. Okay, so here like we are representing the displacement. Similarly, here we represent theta. We have v, here we have omega. Here we have a, we have alpha. Okay, let me tell you one thing. This alpha is not same as ACP, means centripetal acceleration. It's different. Okay, it's not same as ACP. Okay, this centripetal acceleration is basically actually the tangential acceleration. It's the tangential acceleration because we are determining this acceleration with the velocity that you see over here. So you should not get confused. Okay, like here these velocities are changing. These are nothing but the tangential velocity. Agree?
Yeah.
So this particular velocity, the change in velocity, is determining the centripetal acceleration. Okay, that is ACE there, right? Which is not same as this angular acceleration. Alpha is the angular acceleration. Is angular acceleration. Okay, which is different from the centripetal acceleration or the tangential acceleration. Yeah.
Yeah.
Okay. Here we have the formula v is equals to u plus at. Okay. So this is so in this particular case we'll be having omega 2 is equals to omega 1 plus alpha t. The thing is this particular alpha, the angular acceleration, is actually coming into picture because of the varying omega, the varying angular speed. Like it is continuously increasing the angular speed, basically. Yeah. All right. So which is like obviously non-UCM kind of thing. Okay. It is non-UCM. Yeah. So now further, if we write S is equals to UT plus half AT square. So the analogous thing here for the rotational dynamics, we have theta is equals to omega 1t plus half alpha t square. Okay. Then we have v square equals to u square plus 2as. So similarly, we have omega 2 square equals to omega 1 square plus 2 alpha theta. Okay.
So essentially, with rotational dynamics, they just treat different variables as they just essentially represent certain variables in an angular sense.
Correct.
Using the same kind of algebra, because it's like it's hard to describe. It's like saying that a distance is really anything that really just like an amount of something that you want to achieve at a certain rate and given a certain
Absolutely.
time. Like maybe I want to write 500 words and I write at like 50 words per minute. Then
That is the rate.
500, yeah, words is a distance then.
Then in
So-
that case, your distance is basically 50 words. Okay.
Yeah.
Okay. So it's that kind of thing. Though,
Yeah.
okay. By the way, here you saw that like this V is equals to R omega. You can see this, right?
Yeah.
Okay. Now we will be using this thing. You know one thing, that the kinetic energy over here will be equals to half mv square, right? But in this case, this is the translational kinetic energy. Yeah. Here the rotational kinetic energy. The rotational kinetic energy is equals to half m. Instead of v
Half
square,
M, yeah, we can
we
say
can write
omega R.
omega square r square. So what we are bringing in over here, we have half m r square omega square. Okay. Now this m r square thing. Okay. See, we have the analogous term for the velocity over here. Over here we have the angular velocity. Okay. So similarly, there should be some kind of analogous thing to the mass. Okay. In the rotational motion. So that is this mr square. Okay. Which is given the name moment of inertia. Okay. What is I? I is basically known as moment of inertia. Okay. Yeah. So this is basically the moment of inertia. Yeah, which is basically considered to be the inertial thing, the inertia in the rotational motion. The inertia in the rotational motion is not just the mass. It is basically the distribution of the mass. Okay. It's not dependent on the mass when it is rotating. It is dependent on the distribution of the mass. You're getting it from the center.
Yeah.
Now, all these concepts, trust me, like that helps you in understanding like the bigger picture of the universe, actually. Okay. So later we'll actually come to that later. Okay. So the total translational kinetic energy half mv square, rotational kinetic energy half I omega square. Okay. Now the force over here we define as ma. So now since we got introduced to the term moment of inertia, so we can say moment of force or torque, or you can say the force which is causing the rotation, okay, which is causing the change in the angular velocity in the rotational motion is torque, and that is equals to I alpha. Okay. Here we have P is equals to
That
mv.
makes sense. Yeah.
Here we have P is equals to mv. The momentum is linear momentum is mass into velocity.
Yeah, that makes sense.
L is the angular momentum, that is I omega. Okay.
Hang on. What's the means of relating? And then I would assume that angular momentum would probably just be IA over T.
Angular momentum, yeah, definitely. What you can say that
you already put that there.
The torque is basically dl over dt.
Yeah.
So with that you can say dl is equals to torque dt. Okay, and then you can integrate it further. Yeah. So this helps you in determining in understanding basically the third law also. Okay, and the law of conservation of momentum. Okay, let me tell you one thing. Here the law of conservation says that the summation of mivi, okay, is constant, right?
Yeah, no, the only thing like that I'm having a little bit of weirdness with is these are there's a certain intuition I like that I can see with these sorts of values, but at the same time, there's a little bit of intuition missing. So I was just trying to figure out how exactly they derived these equations.
I actually can show you if you know all these derivations on the left hand side. then you can actually determine the derivations on the right hand side, actually.
So the first few are sensible. That's just like
All
a
right. So
very
after which
analogous
one
sort of
you,
relationship.
yeah, after which one you got a bit confused? Tell me.
The rotational kinetic energy, because
And you.
kinetic energy is a scalar value that has to do with the velocity of an object. So does rotational kinetic energy overall describe a different value, or is it the same as translational kinetic energy, just using terms that are rotational?
It is rotational kinetic energy. Basically, the thing is, this rotational kinetic energy is using the linear translational kinetic energy. Now, the thing is, if I consider, suppose, if I consider this particular object, which is rotating, just rotating. Okay. If it is just rotating, then in that case, the rotational kinetic energy is same as the translational kinetic energy. Translational kinetic energy. Okay.
Okay.
Because it is the velocity which is because of which it is having the kinetic energy. So be it the linear velocity or be it the angular velocity, same. Okay. Yeah.
Okay.
So that's what, like here, that's why I wrote half I omega square is equals to half mv square. Now the
Okay, so
interesting
they
part.
describe.
Yeah. Yeah.
Oh, never mind. Go ahead.
Now the interesting part, that when it is not fixed, when it is rolling, then it is bit different. Okay. Suppose if it is rolling, right? It is rolling and then ultimately reaching here. Let's say. Okay. So if it is rolling, then there is some velocity forward as well as there is some angular velocity. Okay. You're getting it?
Yeah.
Then in that case, the total kinetic energy is basically the translational kinetic energy plus rotational kinetic energy. Two different things, actually.
Yeah. Okay.
Now, why they are two different things? The thing is, what would be the speed? That depends on r.
Yeah. Okay. So the angular velocity would be very different. Yeah.
Yes.
Yeah. The speed would depend on the angular velocity, but the overall speed would likely be a lot less than the angular velocity, right?
So then it is different. Yeah. So
yeah.
So that's why the total kinetic energy we can write here. This is half mv square. Okay. Plus this is half I omega square. There are two different things basically. Now the thing is, this I here in this particular case, you saw in the earlier case, I actually got this I to be mr square. Okay. This is fine for superficial understanding. This is I equals to mr square is fine, but in fact, it is having like little more complex definition. The thing is, suppose here this is the axis of rotation. About this particular axis, I'm considering masses. Okay, where is it? I'll actually take a plane, and I'm considering masses like this is m1. Then here we have m2. Okay, then here we have m3. Okay, all these at different distances, r1, r2, r3. Okay, so the thing is and this is a system. This is a system. Okay, so for this, the moment of inertia of this particular system I is actually the summation of mr square from I equals to 1 to n. You're getting it? Do you understand this sigma notation, by the way?
Yeah, 1 second. Yeah, that makes sense.
Yeah. Now, here I have actually given you for the point masses. Like here, all these masses are point masses, isn't it? M1, M2, M3. But what about like when they are like the rigid masses? It's like how about like when it is a disk, when it is actually a disk, when it is a disk. So then there are so many masses. So many masses.
Yeah, it becomes basically impossible to distinguish a sort of linear velocity by which to describe kinetic energy, I guess.
Yeah. So then we have to integrate. Then we don't use the summation. we basically take a very, very small mass around it. Okay, around it we take a very small mass. Okay, and then we integrate it to determine the moment of inertia of this rigid body. Okay.
Oh,
See, the
I
summation
think I
is
see.
used.
No, I see what you're saying. I see what you're saying. Essentially, because of all the point masses. Because the thing is, no, but integration would use the derivative change of one value, right? And we're looking
See,
at two unknowns, which, or no, we know mass, we know radius. Okay, so we use like minuscule amounts of mass at different radii.
yes. Yeah. So
Okay.
I'll actually give you one. Do you know integration and derivatives? All that stuff, right?
Not integration. Derivatives we've started in class, but integration's still a little bit alien to
Okay,
me.
let it be then. Then just I'm just telling you that like you basically determine the moment of inertia of a very, very negligible mass around it, infinitesimal mass basically around this particular axis of rotation. Yeah, and then you integrate it from 0 to r. Okay, right? So that gives you the moment of inertia of this rigid body, of this whole body. You're getting it? So this
Yeah.
moment of inertia is different for different shapes. Okay, like moment of inertia for ring, for the disc, for the rod, for the cylinder, for the sphere. All these are having different moment of inertias. You're getting it?
Yeah. Yeah.
Okay, so yeah, so basically coming back to this total kinetic energy. So this rotational kinetic energy depends on the shape of the object also, because this I is dependent on the shape. Okay. Last year, one student from your school itself, I think it was Emmy, Arun's friend, like someone with Emmy, whoever, let it be, doesn't matter. The thing is like she did an IA, like how the kinetic energy of a rolling object changes with its shape. Okay, means like if you're taking a sphere on an inclined plane, how its kinetic energy is changing. If you're taking a cylinder, how its kinetic energy is changing. So all that thing can be easily actually determined if you know the rotational dynamics properly. Yeah.
Okay.
Okay. So going ahead. So basically, so I hope you understood like this particular thing, right?
Yeah.
All right. Then after that, we have F is equals to ma. Analogically, we can actually get torque equals to I alpha. Yeah, because torque is something which is producing the angular acceleration. Yeah. Similarly, we have this momentum P is equals to mv. So similarly, we have L is equals to I omega. Okay.
Yeah. Okay.
Yeah. Okay. All right. Now, the thing is, so if you consider, suppose a rod like this, okay, if you consider a rod like this, so from its center, it is having some specific moment of inertia. I is equals to ml square by 12. I know the value actually, but from its end, it will be having different moment of inertia. Why?
Sorry. What was moment of inertia? Moment of inertia is mr. Oh, so the L in this case is just
the length of the rod.
And then over 12?
Yeah.
But why over? Why over?
Yeah. I can actually show the derivation, but like that requires the integration and all that stuff. So do you know the basic integration, like what is x dx?
I know the basics of like what the process involves, but no, I've not really done any sort of integration by hand.
You know integration of x dx?
Integration of x dx.
X with respect to x. No. Okay, then let it be. Then we can't do the derivation. This is the simplest thing.
No, just no, it's fine. I mean,
no problem. So doesn't matter. Anyways, like what we are learning is in fact
but the
in
thing
IB
is,
also it is given very superficially.
Doesn't the integral of x dx also have to have like a range, a limit to it?
Yeah, if I give you the range, like suppose, okay, 0 to L x dx. Okay.
0 to L x dx, I mean, x is linear, therefore the area under the curve will be a triangle with base 0 to L, and then, yeah, I mean, if the function is x equals y, then between 0 and L, we take a maximum height, of course, of L. So then it's 1/2 into L squared. Is that right?
Superb. Good. Very nice. That was like little impressive, actually. Very nice.
All right.
All right. So, so the thing is, basically, this I is equals to ms square by 12. That is also obtained using the similar idea. What's the idea over here? Idea over here is like, let's say this whole thing, the entire rod has a mass of, this mass is m, let's say, okay, and the length is L as given. So what is the mass per unit length? Mass per unit length, that will be equals to m over L. Let's say this is lambda. Okay.
Okay.
For now, we are just giving this lambda.
Yeah, yeah.
So lambda at a distance of dx, we have certain mass, right? So that mass will be equal to mass in dx will be equals to m over lambda dx. Agree?
Mass and yeah.
Mass in dx will be lambda dx. Yeah. So the moment of inertia will be equal to lambda dx. This is mass
into the
into
angular
x squared,
momentum or angular
x squared.
velocity.
At distance x we are considering. At distance x for that small dx.
Okay. Wait, is this moment of this is a moment of inertia, right?
Yeah, this is moment of inertia.
My bad.
This is moment of
yeah. Okay.
So basically, so this is lambda dx times x squared. That is the moment of inertia for that very small mass, dx of the dx range. You're getting right? So
yeah.
If I want from 0 to L by 2, this is so 0 to L by 2 basically. Okay. Yeah. And then we will double it later. Okay. So basically, this I will be equals to integration of this lambda is a constant x square dx. Correct. So this will be coming out to be, yeah. So this is the integration of x square dx would be x cubed by 3 actually.
X cubed over 3.
Yeah. So x cubed over 3 from 0 to L by 2. Okay. And that will be coming out to be lambda times x cube, that is so L cube by 8 times 3. Yeah. Correct. Do you understand this?
No, I don't. I mean, I don't understand integration perfectly, but okay, yeah.
Let me tell you something. You said x dx is equals to, you were able to say this is x square by 2, right?
Yeah. So
actually there is a formula.
Basically the opposite sort of. It's an anti-derivation function.
There is a formula. I'm just.
But no. I see what's going on. Essentially, it's x to the n plus 1 over n, or n plus 1. Sorry.
So I actually did the same thing. Okay, and then I'm applying the limits. So then I'm applying the limits actually. Okay. So so what do we get? X cubed by 3. I'm applying the limits. It becomes L cubed by 8 because x is L by 2.
Yeah.
So L cubed by 8.
Okay.
And that is there.
Okay. Yeah, that makes sense.
What is lambda by the way? What is lambda by the way? Lambda is
m over L. So if we have an L cubed over there, then it's
so we have ml square by 24.
L squared over 2.
Now this is for the half part, right? I actually went from
So then we multiply it by 2 to give us the full moment of inertia.
So ml square by 12. This is how we actually get the full moment of inertia. You getting it? Okay.
Yeah.
So this is how we basically determine. This is how we actually use the calculus to determine the moment of inertia. Okay. Now same way. Trust me, like it's fun actually. It's fun to determine the moment of inertia of all such objects. Okay, using the
seems like
calculus. Yeah. So and then
but
determining.
The thing is that sorry, The only issue that I can see here right now is that mass over length essentially gives us an average mass of per length. What happens if we say
Irregular.
what if it's like irregular? What if we have an object where we have like a
Coming here.
massive metal ring on the outside, and then on the inside
Coming
we
here.
have something like really light?
Yes. See, the thing is, so if suppose you are having irregular mass, okay, if suppose you are having some kind of irregular mass, then the approach is slightly different. Okay, approach is not this way. Okay, then the approach is with the energy. Okay, then in that case, you'll be having the approach with the energy actually. Okay, so what do you do in that case? Suppose here we have the object is over here at this particular height, so it is having certain potential energy. Okay.
Okay.
Yeah.
Yeah.
When it is rolling downward, let's say it is over here and it is rolling. Okay. It is rolling and it is frictionless. Okay.
Yeah.
So then it will be having the linear speed v, as well as it will be having the angular speed omega. Okay.
Okay.
Yeah. So at this particular point, it will be having v and omega. So the total energy, the total kinetic energy will be equals to half
linear
mv square plus half I omega square. So if it is rotating, okay, we can determine omega using the experiment. Okay, and based on the, so we know the total energy, we can determine this by analyzing, by observing. Okay, we can determine omega, and with that we'll be able to determine I also. Okay, for the irregular objects. Okay, for irregular objects, this is how we can actually determine. But there is another way also. There is one more way. Okay, and that is the moment of inertia is r square dm. Okay, so the integration of r square dm. What you can do, you can actually in that irregular object, let's say this is the irregular object. Okay, so in that particular irregular object, what you can actually do is you can make a disk or a sphere kind of thing. Okay, and then you can check how this entire mass is like how far is that entire mass from the center. Okay, how far is this entire mass from the center, how far is this entire mass from the center. So you take all those fractions. Okay, now and then you integrate it. Okay, so you take, the point is, like suppose if I'm having this particular rod, all right, you know that about this particular axis the moment of inertia is ml square by 12. But what if I put a mass over here which is having, let's say, m dash at a distance, let's say l, this is l by 2, half l by 4, let's say. Yeah, so at this particular distance, so then in that case the resultant moment of inertia I net will be equals to ml square by 12 plus m dash l square by 16, like that. Okay.
Okay.
Yeah, so if suppose you are having irregular mass, so we are having irregular mass. Okay, so you need to first of all find out the center of mass. You know how to determine the center of mass?
Sort of.
No. Experimentally, how will you determine the center of mass?
Experimentally, I guess you could just try to balance it on a point. Like that. I don't know.
There is a method, very good method. Okay, it's very interesting method. What you can do is you just take 2 points, point A, and let's say I'm taking point B. Okay, yeah, I've taken these 2 points.
Okay.
What I'll do, I'll take this entire mass and I'll hang it using point A. Okay, like suppose here I have this particular turtle, right? So this is an irregular mass, right? So I'll make a hole. I'll make a hole through at any point, at any random point, I'll make one hole, and at any other random point, I'll make another hole. Okay, through that particular hole, I'll actually try to suspend it. Okay, with the string.
Okay.
With the string, I'll try to suspend it. Right now, however it is getting suspended, okay, you'll be able to basically draw a straight line. with that suspension.
Oh, and the intersection of the 2 points between when
Exactly.
you suspend it,
Yes.
either way. Okay.
Yes. And here, this is how you're suspending. So wherever they are intersecting, that is the center of mass.
Shouldn't the center of mass also be a point at which the rotational inertia on either side is exactly the same?
So yes, exactly. Now the thing is, once you got the center of mass, then from there you can actually determine the distribution of the masses to determine the moment of inertia. To determine moment of inertia, first step is to get the center of mass. Okay.
Yeah.
Yeah. So then you can actually take the patches. Take the patches like I can actually take this patch, or then I can take a different patch like this whole patch. Okay, and then I can actually try to determine the moment of inertia of those patches, those small masses, depending on its density. Okay, so a lot of complicated, complex stuff are there, but like if you learn this thing systematically, it becomes easier. Okay, so it's not difficult to determine the moment of inertia for the irradiated object, though it is not in our scope. Okay, in the scope of IB syllabus, right? So, but like I hope along with the circular motion, with these rotational dynamics, things got clear more, right? Yeah.
Yeah.
This and let me tell you one thing. Even in engineering mechanics, I mean, the engineering physics that you have as the option, and that also we don't have all these things in such detail actually. Okay, so we have like very superficial stuff. Okay, there are 4 parts in the engineering physics. One is this rotational dynamics, then other one is the fluid mechanics. Fluid mechanics is amazing stuff there. Okay, you will be learning about the Stokes theorem, you will be learning about the Bernoulli's theorem, all that stuff. Then you have the wave mechanics to a certain extent. Yeah, that's it. You don't have things in that detail actually. Okay, but anyways, I hope you understood this whole thing.
Yeah.
Okay, then next time I want to actually teach you the vertical circular motion. Vertical circular motion is slightly challenging one. Okay, so because like determining the tension at different points, determining the velocity at different points is the challenging part. Okay, so we'll cover that in the next session along with the gravitation. Okay, yeah.